Good evening, viewers. For today's class, we'll be doing the Markonikov's rule and its mechanism. The rule, as you very well know, states that for an unsymmetrical alkene, the word unsymmetrical means the double bonded carbons should not be similar. This has got two hydrogens, while this has one hydrogen and one R group. Such an alkene where the double bonded carbon atoms do not have similar groups on both. The similar situation, you may say, these are two hydrogens directly attached, this has one hydrogen directly attached. If you add on any identity where there can be a possibility of a negative and a positively charged identity on it, that is, there is a polarity difference in the adding identity, then in that case, the negatively charged identity out of the two adding identities goes to the carbon having lesser number of hydrogens. I repeat, negative to carbon having lesser hydrogens. That would be easy to learn. You need to learn the word negative and lesser hydrogens. Hence, your product would be the X moves to this carbon, the double bond is broken down because you're adding up an HX, while the hydrogen goes to this particular carbon. Hence, instead of CH2, I'll be writing a CH3. That's the Markonikov's rule. I'll give the statement once again. Addition across an unsymmetrical alkene for the adding identity, the more electronegative part of the adding identity goes to the double bonded carbon having lesser number of hydrogens. Mind you, don't count these hydrogens. These are not the directly bonded hydrogens to the double bonded carbon. Your aim is only to see the hydrogens attached to the double bonded carbons. Moving on to the mechanism. As far as the mechanism is concerned, the first step in the mechanism is the cleavage of the halo acid. Hence, you are generating an electrophile. So the first step becomes electrophile is generated. The second step, this electrophile is to be added onto the alkene molecule, which is this. The electrophile here is H+. An electrophile can easily attack an alkene molecule due to the presence of this pi electron cloud. The options are, the A option would be that the pi electron cloud breaks down in a way that this pi electron cloud goes here. If this happens, this particular carbon would get a negative charge, while this would get a positive charge. Hence, this electrophile can only move on to this. This becomes our route A. In the route A, I end up in CH3, CH with a positive charge, single bond, CH3. The positive charge is maintained. The H positive goes towards this carbon, negative and positive neutralized, you end up with a CH3. The second option could have been that the pi electron could have shifted like this. Also, in that case, I call it as route B. This was our route A. In the route B, I would have the electron cloud shifted to this particular carbon. Now, this particular carbon gets a negative charge. Thereby, the proton will have to attack here, leading to CH3, CH already, and an H plus goes here. Your double bond is broken down. Electrons have gone to this particular carbon. This particular carbon is left with one electron less, so you get a positive on the terminal carbon. In this route, this is a 2-degree carbocation, while this is a 1-degree carbocation. I hope it is clear that out of the two processes, we would advise an A, which is the correct way of doing it. This is not going to happen because it is leading to a 1-degree carbocation, which is always less stable. Just a recall, why is a 2-degree carbocation more stable? Is due to the electron pushing effect of the methyl groups towards the positively charged carbon due to something known as the inductive effect, called as the plus I effect. Thereby, the step 2 becomes this and not this. Moving on to the step 3. In the step 3, you are left with your X minus and the product formed of the step 2. The step 2 product was a CH3, CH positive and a CH3, and you had an X minus left over from the step 1, which goes and completes the final product, giving you, as you can very well see, your final product here was this, and your final product which you obtained is this. So the mechanism becomes complete. The reasoning here is, why does it not attack here, the electrophile, is because of the formation of a 1-degree carbocation, which is unstable, while the 2-degree carbon cation is comparatively stable. Thank you.